This last video for chapter 6 is my favorite of all time, and it's applications of trigonometric modeling, and it does not appear in your textbook, which is, I feel like, a huge travesty because it's so amazing. It's taking real life circular things like Ferris wheels or a tire turning or, you know, not even circular, but anything with like a periodic nature, anything where something repeats over and over again, like a piston going up and down, or a spring going up and down, or a tide, or a heartbeat, or anything like that. We can take this scenario that's cyclical in nature or periodic in nature, and we can model it using a sinusoidal function, so either sine or cosine. So that's what we're going to be doing here. So the only practice with this is in the worksheet I gave you, and I'm going to focus mainly on Ferris wheels, but do a couple other examples as well just to show you how they relate. But I'm trying to keep this a little bit introductory, so keeping it a little bit easier than it could evolve into. So what we're going to do first off, which is something that you'll never do on a test or a quiz, is I'm going to take words and I'm going to make it into a graph. And I'm going to do this just to show you sort of how we're going to come up with the equation of a sinusoidal function. So for this first example, we have a Ferris wheel that has a diameter of 30 meters with a center 18 meters above the ground, making one complete rotation every 60 seconds. This is all the information we need to make a graph of this sinusoidal function and then come up with its equation. So the first thing is I'm going to draw you a Ferris wheel. So this is going to be quite a rudimentary Ferris wheel, but here's like the ground. And then we're going to have this Ferris wheel, which is a circle above the ground. That is not to scale at all. Let me maybe make it a bit lower. Let's go like this. Okay. So what do we know about this Ferris wheel? Well, we know this Ferris wheel has a diameter, which goes from one end of a circle to the other through the center, of 30 meters. We also know that the center here is 18 meters above the ground, and we know that it makes one complete rotation every 60 seconds. Okay, so again, we're thinking of our, circle functions, right? Circular functions. So when we built these, we always went, okay, all of our graphs started here and then they went around one full rotation. And we're going to be looking at how those features relate to these features. Well, the first thing is that this unit circle that we always drew, you know how we had a point 1, 0, and then we had a point 0, 1. How does that relate? Well, if I put an x-axis in here, we know that the diameter is 30 meters, which means the distance from the center to the edge of the circle is 15. That means that the radius of this circle becomes the what of my sinusoidal function. Can you think of it? It's your amplitude. Your amplitude is the radius of your circular function. So if you watch that preliminary video that I showed, I didn't show it for you, but if you clicked on it or put in the link, it was showing these circles with these different sizes and how that led to different amplitudes. So what it is that our circles always had an amplitude of 1 because we drew unit circles. This circle has an amplitude of 15 because its radius is 15. Okay, what else? Well, we also know that it has a center 18 meters above the ground. So this center point is 18 meters above the ground, which means that the lowest point of this graph is 3. So it's going to have this center point at 18, and then it's going to go 15 meters up from 18 and 15 meters down from 18. So my lowest point would be 3, and my highest point would be 15 up from 18, which would be 33. So this graph is going to go down to 3 and up to 3. Well, what is this giving me? The fact that my center of my circle is 18 meters above the ground is giving me my d value. It's your vertical displacement. All right, well, what about C? C we're going to leave for a while, okay, because it depends upon which sinusoidal function you pick. But the next thing we're going to move on to is B, which I could have done second as well. But we want to know, like, we're coming up with sinusoidal equations. We want A, B, C, D, right? That's the whole point. So our whole point is to come up with y equals A, either cos or sine, B, x minus c plus d. Okay, so far we've figured out A is going to be the radius, D is going to be wherever the center of your circle is, or the center of your oscillating piston, or whatever it is. And now we have to figure out B. B is always 2 pi divided by the period. Well, did they give us the period of this? It tells us that it takes one complete rotation every 60 seconds. So to go from bottom back to bottom again, or let's relate it to our unit circle, to go all the way around our circle takes 60 seconds. Well, normally, to go all the way around a circle takes 2 pi radians, or 360 degrees. And instead, we're saying that it takes 60 seconds. So in this case, our period is time. And so this is going to be, the period is the time for one cycle, or in our case, one rotation of a Ferris wheel. Okay, now technically you have enough at this point to come up with the equation of your sinusoidal function, but just for the first time I want to show you the graph because it's so much easier to see why we pick the thing we do and sort of where everything comes up from. So we're going to put our axes in. So since your height is always going to be above this ground, this is not a paddle wheel, right? So another good application, I just remembered, is a paddle wheel. So those like old ships where like they had a big wheel on the back that would push the water, and that's what propelled you forward, right? So that's an example of a Ferris wheel but below the ground, right? Because it goes below the water. But all of Ferris wheels that we go on do not go above the ground, otherwise that would be scary. So we're going to keep everything above the ground, and we're going to keep everything in positive time, or sorry, positive x-axis. So the next thing I want to talk about is the fact that we are moving into this real life application. So when we do function like modeling with y and x, it has no context beyond y-axis and x-axis. As soon as we put it in an application, we want to know what the y value is representing. What is the x value representing? So if we think of this Ferris wheel, I already kind of talked about the x-axis. The x-axis is your time for one cycle. And so your x-axis is representing time in seconds. Well, what about your y-axis? Well, over time, what's happening? If you think of a person riding the Ferris wheel, over time, what is changing? They go from 3 meters to 18 meters to 33 meters. It's their height. We are going to be looking at height in meters as a function of time in seconds. Okay, so now what we're going to do is we're going to draw the graph of one complete cycle. Now here's your big assumption, and every single one I ask you, I think, if I'm remembering correctly, this is the assumption we will always make, is that the rider starts at the lowest point, which for a Ferris wheel, I don't know how they'd enter any other way, right? You walk up to the gate and they let you on the Ferris wheel, and then you go around and around, right? You can't enter midway up because that would be a really long ladder. So we're going to have our rider start at the bottom point. So the bottom of your graph is at 3 meters, and the highest point of your graph is going to be 33 meters. So I already know that this is 20 grid lines. So we have to go up to a height of 33 in 20 grid lines. And so I think that gives us 1.65 or something. 33 divided by 20, which means our scale has to be at least 1.65. So I don't want to pick 2 because 33 and 3 don't go into 2. So I'm going to do a scale of 3, which is a little bit unfortunate. I wish I could spread it out a bit more, but I'm going to make every grid line worth 3. So it goes 3, 6, 9, 12, 15, 18. 3, 6, 9, 12, 15, 18. Yeah, so 18 is right there. And then 21, 24, 27, 30, and then up here is 33. So I'm not going to really maximize this grid, but that's okay. And then for time, I know I have to make it all the way to 60 seconds. Again, there's 20 grid lines here. So we're going to make each grid line worth 3 seconds. So every grid line is going to be worth 3. And then we're going to go 3, 6, 9, 12, 15. Ooh, let's talk about why I'm putting 15s on here. If my period is 60 seconds, then my key points, there's going to be 4 key points. Remember, this is a sinusoidal function. There's going to be 4 of them in that 60 seconds, so they're going to happen every 15. So that's why I'm putting 15s on here. So that was how many grid lines? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, I'm up to 30. 1, 2, 3, 4, 5, I'm up to 30, 45. And 1, 2, 3, 4, 5, I'm up to 60 seconds. Okay, let's graph this. So assuming that my rider starts at the lowest point, it means at 0 seconds, they're at a height of 3 meters. Now, every 15 seconds, they're going to go through the rotation. So at 15 seconds, they're going to go up to the midline, right? So we've started at the bottom, we're going up to the midline, and then we're going to go up to the top. So at 30 seconds, they're going to be at the top of the rotation. So here, and then they're going to come back down. So this is 15 seconds into it. This is 30 seconds into it. This is 45 seconds into it. They're back at the midline, or 18 meters. And then lastly, at 60 seconds, they are down here at 3 meters. So this is one complete rotation of that Ferris wheel, modeled in a two-dimensional model. All right, so now from here, can we come up with our sinusoidal function? So instead of being y, so remember our original equation is y equals a cos or sine of b x minus c plus d. Okay, so now we're going to be modeling this as a function. So it's going to be height as a function of time. So y is height as a function of time. It's going to equal. Now we're going to fill in the a value. We're going to pick either cos or sine. We're going to fill in the b value. Our x is now time. We're going to fill in the c value, and we're going to fill in the d value. So what are we going to do? Well, we already determined that the amplitude is the radius. So our amplitude is going to be 15. We'll talk about whether we're picking cos or sine for a second, but let's talk about our b value. So again, a is the radius, which equals 15. B, we already set up here. I don't know if I explained that actually. So what it is that period is normally 2 pi divided by b, right? We know that. So whatever the b value in our equation is, 2 pi divided by b gives us our period. Well, we can go the opposite way around. If I wanted to solve for b, I could multiply b on both sides. I get pb equals 2 pi, and I get b equals 2 pi by p. So to find the b value, you're always going to do 2 pi divided by the period. So for us, it's going to be 2 pi divided by that 60 seconds. So I'm going to put it in a simplified fraction. Some textbooks don't simplify, which I find weird, but I'm going to. So I'm going to put it in as pi by 30. I'm going to skip phase shift for a bit, and I'm going to say that D is your center. So for our example, our center line happened at 18 meters. So I'm going to put plus 18. Now, to figure out C, you have to decide whether you're looking at cos or sine. So if you look at this graph, if you made this a cos graph, okay, so if we chose cos, it would be h of t, h of t equals. Normally a cosine graph starts at its top and then goes through the cycle, but this graph's starting at its bottom. How can we reflect our point from the top to the bottom? Maybe we're reflecting the y values over the x-axis, which means it would be negative 15. So if we choose this as a cosine function, we can put negative 15 cos pi by 30. Then we don't need a phase shift because you're starting at the bottom. So you can just do cos of pi by 30t plus 18. If you were to do this as a sine function, which I don't recommend, right, you're looking for where it's at the midline and heading up. So in this example, we're looking for our first key point because here it goes up. So if you were going to do this as a sine function, you would have an a value of 15. You'd put it as sine. Pi by 30 would still be b, but then you'd have to do a phase shift to the right 15 plus 18. So I highly recommend choosing the cosine function. It's the one that I would choose every single time. It's just easier, and I'm going to make riders start at the bottom, so it makes it really easy to do. All right, then we can actually use this function. So now it can ask you questions like, what is the height of the rider at 52 seconds? So we're going to plug in time is 52. So you're going to find height as a function of 52 seconds, which would be negative 15 cos of pi by 30 times 52 plus 18. Now the important thing is, because we did 2 pi divided by the period, our calculator has to be in radians. And sinusoidal functions are always modeled in radians, so just make sure that your calculator is in radians. Now let's plug it in. So for me, I'm going to go 15 negative times the cos of, so I'm going to go bracket, and then I'm going to plug in pi divided by 30 times 52, unbracket, plus 18. And that gives me, it didn't tell me what to round to, so I'm just going to go, I don't know, 2 decimal places. So 7.96 meters. So at 52 seconds, so if I went up to this graph, 52 is like 48, 51, so 52 is somewhere in here, right? If I go up at 52 seconds and I go over, it's at about, 8 seconds, right? Okay, and what about this next one? This next one, I decided not to put a question like this on the test because I'm like, it's good, but I don't know. There's just only so many questions I can ask you, but it's kind of a cool one. So instead of giving you time and asking for your height, it's saying find the time at a certain height. So this time, in your equation, h of t is equal to negative 15 cos of pi by 30 t plus 18. This time they're giving you height. So in for height, you're going to put 20. So 20 equals negative 15 cos pi by 30 t plus 18. And now legit, you are just isolating t. So if you think of solving any linear equation, right, the first step we're going to do, actually I'm not going to change colors all the time. First step I'm going to do is minus 18 from each side. I end up with 2 equals negative 15 cos pi by 30 t. Now again, I'm trying to get into the t, and remember this is not cos times pi by 30t, it's cos of pi by 30t. So that's the last operation you're going to do, is like try to get into that t. So the next thing you're going to do is divide by negative 15. So 2 divided by negative 15 equals the cos of pi by 30t. Now think of inverse operations. If I now want to get rid of cos, I'm going to take the inverse cos. So I'm going to take the inverse cos of 2 divided by negative 15 equals pi by 30t. And then lastly, to get t, I'm going to do inverse cos of 2 divided by negative 15 times 30 divided by pi. So for me, I'm going to take the inverse cos bracket, I'm in radians, 2 divided by negative 15 unbracket, times 30 divided by pi equals, and again, let's go 2 decimal places, I guess. So let's go 16.28 seconds. So this time, to reach 20 meters, and this gives you the first time you reach 20 meters. So, that's a whole extension on these questions. But whenever you solve algebraically, it will give you the first answer. And so it's telling you that at 20 seconds, so like 18, 21, so somewhere right before here, that you're at a height of 20 meters. Sweet. All right. So what I would recommend doing now is pausing the video and trying the next couple examples. Okay, but I'm just going to keep going. So this is another Ferris wheel question. So Joy is the last aboard a Ferris wheel at the county fair. The loading platform is 2 meters above the ground. The Ferris wheel has a radius of 8 meters and completes 1 revolution in 48 seconds. So the first thing I'm going to do is draw myself a Ferris wheel. I find it always just sort of gives me context. So here's the ground, there's your Ferris wheel, it's got its nice little axes in there. What are they giving us? Well, they tell us that the loading platform is 2 meters above the ground. Now that's not telling us the center, it's telling us the bottom. So the bottom of your graph is 2 meters above the ground. Then it says the Ferris wheel has a radius of 8 meters. So I'd put an 8 here and I'd put an 8 here. Now don't forget A, which is your amplitude, is always equal to the radius of your circle. So in this example, A is going to be 8. And then we can move on to, I always go to D next. I know it's at the end, but it's related to it. D is always your center line, right? So where's the center line? Where's the center of your Ferris wheel? Well, the bottom of the Ferris wheel is 2 meters off the ground, and then another 8 would take you up to the center line. So your center line is up 10. Right? So the bottom of your graph's at 2, the center of your line's at 10, and then the top of your graph would be up here at 18 if we were sketching it. And then B is always 2p divided by the period. And for this equation, it completes 1 revolution in 48 seconds. So 2 pi divided by 48, which simplifies to pi over 24. Okay. Now, the next thing I want you to think of is the fact that you are loading at the bottom of your Ferris wheel. So again, I'm going to use cos. So we're going to go h of t equals negative 8 cos pi by 24 t plus 10. right? So if you thought of this, it's the person loading at the bottom. So this is what it looks like. The bottom point's at 2, the top point's at 18, the center line is here at 10, right? We're starting at the bottom, so we do a reflection of the y values over the x-axis, and that's it. That is my equation. Nice and simple. This last example, they're going to give you the equation. So this is an example of modeling tides. So by using the average of high and low tides, the depth of water in meters in a seaport can be approximated by this sine function, where t is the time in hours. So what they've done is they've taken something and they've said, hey, let's look at the depth of the water over time. And they've decided that, maybe it goes something like this. Okay, and then they've translated all of this information into this equation to have depth as a function of time, where time is in hours, so be careful. And then we're going to ask you questions about this equation. So this first one says, what is the period of the tide? In other words, what is the time for it to get from one low tide to the next low tide? Okay, that would be one period. So we're looking from where it has one low tide to another low tide. Well, we know that period is 2 pi by b, right? So this is just like the questions we did before this. If you ever want to know period, you figure out whatever the b value is and divide it into 2 pi. So it's going to be 2 pi divided by 0.164 pi. You just put the pi in there. And then the pi's simplify. You're left with 2 divided by 0.164. So 2 divided by 0.164. And that gives you, let's say to one decimal place, 12.2 hours. So this is actually how it works. Tides are never, it'd be so nice if tides were 12 hours apart, because then you'd be able to time tides. Like every day you'd go out there and be like, the high tide is at 6, the low tide is at 12. But instead it's this 2.2 hour cyclical cycle, which is why your tides change every day. Okay, next question. The next question is, what is the depth of the water at 2 hours into the tide cycle? Can you pause your video and figure this out? What are they giving you? What are they solving for? So for this one, then we want to know the depth at 2 hours. So into your calculator, you've got 2.5 times the sine of 0.164 pi times t is 2 minus 1.5, all plus 13.4. It's just an exercise of plugging in your calculator. So make sure you're in radians. And then we plug in 2.5 times the sine of bracket decimal 164 pi times 2 minus 1.5 is just 0.5 unbracket plus 13.4 equals. And I get the depth of the water at 2 hours is 14.04 meters. This next one is, what is the range of the depths of the tide? In other words, again, if this is sort of what my model looks like, I'm just totally guessing what it looks like. We could have graphed it. We're looking for how low does your tide go? So remember, its depth is a function of time. So how low it goes up to how high it goes. So what's your lowest point and what's your highest point? Well, think about your range. So your range is always the center line plus the amplitude and minus the amplitude. So if we do that, let's do that. So d minus a all the way up to d plus a. So my center line is 13.4 meters. That's ugly. 13.4 minus my amplitude is 2.5 all the way up to 13.4 plus 2.5. Plugging that in, I get 13.4 minus 2.5, which gives me 10.9 meters. So 10.9 meters is the lowest depth. And then the deepest depth would be 13.4 plus 2.5 is, whoops, not times, 13.4 plus 2.5 gives you 15.9 meters. So the range of your tide is from 10.9 meters up to 15.9 meters deep. So these questions only exist for practice on a worksheet. They are not in your textbook, but they are so great. The last video here, I can't recommend watching enough. It's called a Rubens tube, and it's this super old school hippie looking physics instructor showing you how sine waves work. So he creates a Rubens tube is something where you have like a PVC pipe and you put gas through it, and then there's holes drilled into the PVC pipe, and so that and then you light it on fire. So the gas comes through the holes and the flames come out of the holes, and then he blasts music through the tube, and so it makes a standing wave. So music has a certain frequency or a certain number of cycles per second or per length, and depending upon the tone it changes your standing wave, and you just get to see flames dance, and it's super cool if you then think of that being a sinusoidal function. So don't forget as well, in your journal you get to choose from the prompts, and one of the prompts is choose a field that you're interested in, science or music or electricity or mechanics, right? Pistons going up and down, and see if you can find an application of a sinusoidal function. So this Rubens tube is a really awesome one. And so things you could talk about is how changing the tone changes the amplitude. You can decide how deep you want to go, but I want to see some of the language like period or amplitude or phase shift or displacement, something along those lines when you're talking about an application. Good luck.